This is your Captain Blake Goebel speaking. He will tell you about calculus of world traveling, and I'm assisted by my flight attendants Bailey Olson and Taylor Daniels. So our motivation to do aviation and world traveling is that Bailey's interested because her mom has her pilot's license, and Taylor likes to travel, and I'm the male in the group, so I didn't have a choice. Alright, so history on planes. Orville and Wilbur Wright created and tested the first plane made, and this happened in Kitty Hawk, North Carolina. Wilbur's first flight lasted about 4 seconds, and he went about 112 feet, so he averaged about 28 feet per second. Orville did the second flight, lasted about 12 seconds, went 120 feet, and averaged out at 12 feet per second. And then here are two pictures of planes that were planned out. This one was by Leonardo da Vinci in 1490. The other one was Sir George Cayley in 1799. Some discoveries while we were doing our research, we found that planes have to do with the velocity function, which is flight paths, and also for pilots to avoid collisions. Optimization would be our ticket pricing, and then area under flight angle, you find the perfect area of airflow below the wings. Now, history of the velocity function was by Sir William Petty. A few works of his were in 1662, he made Treatise of Taxes and Contributions, and in 1664, he had Verbum Sapienti. And then, what he originally used the velocity function was to estimate the amount of money necessary to support the commercial activity of a nation, and also found that stock equals the small part of national expenditure. Now, we will also be using Riemann sums in our discoveries, and that was founded by George Frederick Bernard Riemann. He explained the Riemann integral using Riemann sums and developed a theory of trigonometric series, which was a step in generalized function theory. He developed it in 1851, but it was also influenced by Gauss and Weber.
A little history about optimization. For Matt and Lagreg, they found calculus-based formulas for identifying optima, which is just like that topper. And then Newton and Gauss proposed iterative methods for moving towards an optimum, which are just different ways of finding that point again. Now for the fun part. For all of our problems, we used one specific plane just to keep consistency. And this plane is a Boeing 747-8I. I stands for Intercontinental. This plane has 362 person maximum. It has 3-class configuration of economy, business, and first class. And it also has 2 decks. And for all of our problems, we used 570 miles per hour as a constant cruising speed. So what we wanted to do is we wanted to figure out if it was possible to travel the world in 5 days and hit all 7 continents. So we came up with a plan to travel from city to city. Where we started was Minneapolis, and then we went to Brasilia. And the original plan was to skip Antarctica because they thought there weren't any airports there. Turns out there's like over 40. And so we were going to skip Antarctica and go from Brasilia to Sydney, Australia. But then we talked to Bailey's mom, and she said that was impossible, and we would land in the ocean before we got there. So we decided to make a pit stop at the South Pole. And then from the South Pole, we go to Sydney, Australia. From Sydney, we go to Agra, India. From Agra, we go to Cairo, Africa. From Cairo, we go to London, Europe. And from London, we come back to Minneapolis. So in order to figure this out, what we did is we rearranged the velocity function to solve for time. And once again, we used that 570 miles per hour as the constant speed. And we looked up all the mileage by like bird flight, other colors. And from Minneapolis to Brasilia, it was about 4,800 miles at 8.5 hours. Brasilia to Antarctica was about 3,300 miles at 5.8 hours. Antarctica to Sydney was 7,500 miles at about 13 hours. Sydney to Agra was about 6,000 miles at 11.2 hours. Agra to Cairo was 2,800 miles at about 5 hours. Cairo to London was about 2,000 miles and 3.8 hours, and finally London back to Minneapolis was about 4,000 miles and 7 hours. So we found that we could do it, and we added all the hours up together, and we got 54.641 hours, which equaled 2.277 days. But we wanted to make this a little bit more realistic, and so instead of having a plane go from one city to one city to one city, because they're not going to just switch that fast and take off. So we added 3 hours between each flight, that'd be typically used for boarding, unboarding, refueling, and maintenance and cleaning and stuff like that. And we found that we still could do it, and that took about 75.6 hours, which is equal to about 3.152 days. And this is just a photo I photoshopped of us partying on a plane with Simon Cowell because we made it around the world in 5 days.
Okay, so being the responsible travelers that we are, we needed to find our flight range just in case we had a quadruple engine failure. We wanted to make sure we were prepared. Okay, so to find our approximate area that we could cover if we had a quadruple engine failure, we would then be known as Glider 1. And so we used right and left rim on suns to approximate the area we could cover before we would start praying and hoping there was an airport nearby.
And that was equal to about...
We found using a right rim on sun, it was an underestimation of 172.5 meters squared, and with left rim on suns, it was an overestimation of 175.5 meters. Or miles, miles. Okay, so with revenue optimization, for 300, or on a plane, if we have 300 passengers on the plane, the price per ticket is $880, but then once it goes over 300 people, there's a $1 deduction from the fare price. And so we wanted to find the maximum revenue for our airline. So R represents our equation that we use to find our optimal revenue. With 300 people on the plane and a ticket price of $880, we added Y persons and subtracted Y dollars and found the derivative of that equation, set it equal to 0 to find our maximum number of people on the plane that would bring in our optimal revenue, and that equaled 250 people on the airline, which would make about $346,500. But we were like, what? This doesn't make sense. Why would an airplane be able to hold 362 people if at 250 it's making its most money? Well, with 3-class configuration, 880 is just like a average ticket price for the plane, and so planes make their money by boosting up the prices on the higher classes.
Some other applications that we found throughout our research was for the velocity. We found they use it in NASCAR, like when they're going in pit road, there's a certain speed that they have to maintain or else they get into a lot of trouble. And NASA uses it all the time with their science and engineering and technology. And athletics uses it a lot with like speeds of balls, speeds of athletes, how fast people are running, and stuff like that. And they use it a lot, the velocity function a lot in weather to how fast like hurricanes are moving, how fast tornadoes are moving, just storms in general, how fast they're moving. And for the integral, NASA uses it as rockets take off. They find the area underneath, so to see how much thrust is being pushed down. They use it in electricity because the work function is an integral. Crash tests. Here's an example up here. The first crash test, it has a lower area underneath the curve, which means that the impact was focused in one major spot, versus the second crash test. It has a larger area under the curve, which means the impact was spread out a little bit more, so the acceleration felt by the car that was hit is less than in the first crash test. And integrals are also used in wave functions of music when finding the area underneath the waves. And for optimization, they also use it in like fencing and construction and house building. And an example of the house building is when they hang lights to see how much area, the maximum amount of area they can cover with that light in the specific spot that it's at. Any questions?